Yep. You hear me? You want me to record, right?
Sure, I will quickly
Go ahead.
go over it. Can you guys hear me?
Yes.
Can you
Yes.
guys hear me? Okay.
Yes.
Hi, everybody. Thank you for coming to Rabie Fadil's PhD defense today. So he will be doing a presentation, which is going to be less than 40 minutes. Then we'll have the first round of questions from the committee members. Then this is open for the audience for questions, both online. If you have questions for people online, you can put it in the chat and I'll be checking the chat as well. And I'll make sure that your questions will be answered. Then we need to ask the audience to leave the Zoom and the people who are here. And the committee can ask their second round of questions. And then we will ask Rabie to leave. A decision will be made and we'll ask him to join us back to give him the decision of the committee. And the decision can be a minor revision, major revision, and rejection, or no revision at all. So yeah, look forward to the talk. I'm recording this for to make it available to other students. Rabie has already agreed to that. So we'll go from there.
Yeah, it's recording, right?
Yes.
You see my screen? Awesome.
Yes, it's great.
Well, hello everyone. It's a pleasure to be back to campus and to see you again. I'm sorry if this presentation was scheduled in the morning, especially for our collaborators at Simon Fraser University. I would make sure to make it as entertaining as possible. As you can see, my dissertation is about the assessment of blood pressure and posture control mechanisms in Parkinson's disease during an orthostatic challenge. So this is the outline I would be following in this presentation. First, I would start with a background, then list the goals and objectives of this work. Then we would talk a little bit about blood pressure and postural control to put you in context, then represent the methodology and the four contribution of this work. And finally, list some limitation and future work. So as you know, Parkinson's disease is a neurodegenerative disease that affects body movements, and especially it's the impairment of the area that controls those movements. And the kind of the mechanisms that lead to that impairment involve genetic factors and environmental factors. So genetic factors are characterized by the mutation of certain genes, such as synuclein alpha, and environmental factors include head trauma, pesticides, and drugs. Like this. What? It should work. Sorry about that. It just.
Yes, it was working.
Okay. So the main motor symptoms of Parkinson's are tremors, stiffness, bradykinesia, and postural instability. However, other symptoms of non-motor nature could manifest in Parkinson's, and those are fatigue, constipation, dementia, and orthostatic hypotension, which is the focus of this dissertation. So orthostatic hypotension, it's basically a drop of blood pressure whenever we change position from supine to stand or sitting to standing. It's clinically defined as a drop of blood pressure of at least 20 millimeter of mercury or 10 millimeter of mercury diastolic within 2 to 5 minutes of standing, or during a head-up tilt test at 60 degrees. Orthostatic hypotension is very common in people with Parkinson's disease, and its incidence rate is 20 to 50% in the patients. The symptoms of orthostatic hypotension include dizziness, fainting, weakness, and blurry vision, as well as nausea. it's about 45 to 68% of people in Parkinson's disease experience a fall each year. The consequences of falls are devastating and can lead to restriction of activities and fear of falling, as well as inducing caregiver stress, hospitalization costs, while 50 to 86% of people who experienced a fall in the past will also experience a recurrent fall in the future. So, as I mentioned before, orthostatic hypotension is very associated with Parkinson's disease, but it also can happen in elderly population in general and in astronauts upon their return on Earth from a mission to space. So, for instance, most of this work could also be applicable to prevent orthostatic hypotension in astronauts. And most of the methodology is inspired from aerospace studies, which we have in collaboration with Simon Fraser University in Canada. And orthostatic hypotension could also happen during hemorrhagic state where someone is losing blood. So this is just a literature review, a short one about the system studied in Parkinson's disease. As you can see, it's mainly cardiovascular system here, posterior and respiratory system. They were studied independently in Parkinson's disease. However, studies in healthy people found out that these systems should not be studied in isolation, where there is an independence between the system. So the goal of this work is first to quantify and evaluate the interaction between the cardiovascular system and posterior system, but also cardiorespiratory interaction and posterior respiratory synchronization in people with Parkinson's and healthy controls. So the main goal of this dissertation first is to prevent falls in people with Parkinson by assessing the mechanisms involved in blood pressure control and posterior balance. And the secondary goal is to design a robust system for the tracking of hypovolemia, but also identify people with low tolerance to blood loss. One last thing. So now I would like to talk a little bit about blood pressure and posterior control. So blood pressure is mainly maintained by the cardiac baroreflex. Whenever we experience a drop in blood pressure, such as when we stand, there are certain receptors that detect that change in blood pressure and relay that information to the autonomic nervous system to increase heart rate, cardiac contractility, and also vasoconstriction, all of which they would lead to an increase of blood pressure. Another system involved in blood pressure control is lower limb muscle activation. Whenever we stand, our muscle contracts, and when they contract, they squeeze blood back to the venous circulation, increases venous return and cardiac output, as well as blood pressure. Another system is respiration. During inspiration, when we inhale, our thoracic cavity expands and intrathoracic pressure drops. And part of that drop of blood pressure gets transferred to the right atrium. So the right atrial pressure drops, which leads to increased venous return, cardiac output, and also blood pressure. On the other hand, posterior control is maintained by including sensory information from the visual, vestibular, and somatosensory systems. All the systems will send this information to the autonomic nervous system, which will integrate it and the appropriate motor response to maintain blood pressure and the posterior control. So this is just the methodology we have followed in this work. We have recorded data from Parkinson's patients and healthy control in supine, tilt, and stand. The goal of this test, the tilt test, is to induce orthostatic challenge. Data was recorded at Stanford Clinic in the Parkinson's research lab, and we have obtained an IRB approval both at Stanford and at the University of North Dakota. These are the signals we recorded: heart activity, muscle activity, posterior sway, respiration, changes of blood volume, and also blood pressure, of course. We recruited data from 30 Parkinson's patients and 22 healthy controls. 1 Parkinson's and 4 healthy controls were not included in the data collection because they have lower cognitive function score. This is just an example of the signals. First, we annotated the heart signal to get the beat-to-beat data and RR intervals. Then we annotated blood pressure to get systolic, diastolic, mean arterial pressure, and all the other pressures. For muscle activity, we aggregated all the muscles from the legs to represent overall muscle activation. Then we used a cutoff frequency of 5 hertz to obtain the EMG envelope. And we also calculated the area under that EMG to represent something analogous to impulse of force. And we know that EMG impulse. This is an example of EMG raw data. And this is the EMG envelope on the top and EMG impulse. For posterior sway, we calculated the resultant posterior velocity as the square root of the squared interior posterior medial lateral sway. We also calculated the resultant posterior sway. So these are just the formulas used to calculate those. This is an example of posterior sway in the medial lateral and interior posterior directions. This is an example of the resultant postural sway and posterior sway velocity. And then we were interested in studying the causal relationship between, for example, muscle activation and blood pressure. And granular causality is widely used for that purpose. However, granular causality is only applicable for stationary data and not non-stationary data, such as physiological signals. And it also cannot be applicable if both systems are driven by another process or in case of dynamical systems.
What? I didn't know you were here.
Thus, we use the more kind of complex technique that can deal with the non-stationarity of physiological signal. And this is convergent cross mapping. It's based on space reconstruction. Basically, the idea you can reconstruct the original process using only one variable. So you use a lagged version of that variable, and you have a reconstructed manifold. And then you can reconstruct that manifold using X and using Y. And since those reconstructed manifolds map one-to-one to the original one, they should map one-to-one to each other. So you use, for example, constructed manifold using MX to predict MY and vice versa. And then predicted X by MY is equivalent to X causing Y. And the strength of this causality is basically correlation between the predicted variable and the original one. We were also interested in looking at the frequency content of those signals, and Fourier transform is widely used for that. However, Fourier transform is only, again, applicable for stationary data because it uses a bunch of sines and cosines that oscillates forever. And also, it gives you a pretty good frequency resolution, but you don't have any idea on at what times those frequencies are happening. So basically, it shows you what happens in a signal, not when it happens. And that's why we used a time frequency analysis technique. And this work, we used wavelet coherence transform. And you can see here, so it gives you kind of an idea on what happens in the signal in the time and frequency domain. This is just an example of interaction between blood pressure and heart rate. We were interested in two frequency band, which reflects the responses or the interaction between cardiovascular and posterior system. And we extracted three metrics from wavelet coherence transform, and those are fraction time active. It's basically the time that these two systems are interacting, and this interaction is significant. We also looked at the relative amplitude between the two signals and the active gain, which is a product of kind of the fraction time active and gain. Now I would like to move to the first contribution and talk about the findings. So in this work, this first contribution, we were interested in studying the effect of the cardiac reflex in Parkinson's and healthy control, but also the effect of upper limb muscle activation on maintaining blood pressure. So basically, these are just the kind of the interaction we were interested to, flow of information from muscle activity to blood pressure, but also interaction between blood pressure and heart rate. Again, this is the study protocol. So we studied those interactions in supine, tilt, and stand. This is some results. As you can see here in figure A, the cardiac baroreflex decreased from supine to stand in both groups. However, it's lower here in the red, lower in Parkinson's compared to healthy control. On the other hand, the muscle pump, it's increased from supine to stand in both groups. This is similar to the previous slide. Again, the cardiac baroreflex, this is in the high frequency, decreased from supine to stand in both groups. However, it's lower in Parkinson's compared to healthy control. In this figure, you can see the muscle pump function here. In this figure A, it's lower again in healthy control in Parkinson's compared to healthy controls. And here in figure B, you can see the causal effect of muscle activation on maintaining blood pressure. And this relationship is again lower in Parkinson's compared to healthy control. This figure shows just all the parameters that we have extracted in this work. And you can see here in red, healthy controls have higher values in mostly all the parameters, except for two of them, heart rate and muscle activation, which were not statistically significant between the two groups. So some takeaway from this is the cardiac baroreflex is impaired in Parkinson's patients. And also they have experienced an impairment in the muscle pump function to pump blood back to the venous circulation, increasing blood pressure. And also the effect of the cardiac baroreflex is reduced when we stand because lower muscle activation also contributes to blood pressure. So the cardiac baroreflex function is reduced. Now I move to the second contribution. So in this work, we were interested in studying not just the effect of muscle activation on blood pressure, but also on posterior sway. There is a direct relationship between posterior sway and muscle activation. So this is basically the cardiopostural model, which shows the interaction between the cardiovascular and postural system. And this, again, the interaction we were interested to. So basically, as I mentioned, effect of muscle activation on posterior sway, but also on blood pressure. In this work, we were also interested to find out if those muscle activations are actually activated because of changes in blood pressure or changes in posterior sway. So we wanted to know if muscle activity is baroreflex mediated, which means related to blood pressure or posterior sway. You can see in this figure that a posterior sway is higher in Parkinson's patient, and this is pretty obvious because those patients already have posterior instability and as a motor symptom, so they already have motor issues. But what is interesting is medial lateral sway was higher than interior posterior sway in both groups. In this figure, you can see that the dominant muscle activation during standing was medial gastrocnemius and soleus, and this was in both groups. Again, in this figure, you can see that muscle pump function is lower here. I'm sorry, it's higher. This is in terms of the gain. It's higher in Parkinson's compared to healthy controls. However, the causal effect of these muscles to maintain blood pressure is lower for Parkinson's compared to healthy control. And this is for all individual leg muscles. In this figure here, you can see that muscle activation did not kind of drive posterior sway, nor posterior sway was driven by muscle activation. That just shows that muscle activity did not really have effect on posterior sway in both groups, and there was no changes in the groups. Those diagrams, Venn diagrams, were constructed to gain more information if muscle activity is due to changes in blood pressure or to changes in posterior sway. So for example, here, if you look at SBP to COP, which is interaction between blood pressure and posterior sway, and this interaction is basically through muscle activation. Whenever there is a change in posterior sway, it leads to changes in muscle activity that drives blood pressure. So this is through muscle activity. But here, blood pressure interacts with muscle activity directly without any intervention of posterior sway changes. And you can see that the blue and the green area here, there are areas where they don't overlap, which means that there are areas where EMG or muscle activity driving blood pressure independently of posterior sway. That just shows that muscle activity is baroreflex mediated rather than posterior mediated. And you can see also that the interaction between all the systems is impaired in Parkinson. So the overlap between all of them is lower in Parkinson's compared to healthy control. This just confirms what I just said, that muscle activity had higher effect on blood pressure than posterior sway. You can see here, medial gastrocnemius driving blood pressure is higher than medial gastrocnemius driving posterior sway. And similarly for the other muscles. And this is for Parkinson's and healthy control. So in summary, we found that the driver of muscle activation is blood pressure rather than being posterior sway. We also found that muscle activation has higher effect here on blood pressure than on posterior sway. And finally, the cardio-postural interaction are impaired in Parkinson's, and the contribution of leg muscles is more for posterior balance than for blood pressure. So in this third contribution, we were interested in studying the effect of respiration on posterior balance. There's a direct relationship between respiration and posterior balance, and this relationship happened through different mechanisms. First, whenever we breathe in, the movement of the diaphragm and rib cage induce variation in posterior balance. But also during hyperventilation, there is a reduction of carbon dioxide, which leads to a vasoconstriction response, a cerebral vasoconstriction response that could lead to dizziness and posterior instability. And finally, breathing was also shown to affect the cerebral cortex and altering activity of upper limbs and lower limbs. So these are the interaction. Again, we were interested to basically effect of respiration on posterior sway, but also on muscle activation. I just want to mention here that we studied this in people with orthostatic hypotension and Parkinson's without orthostatic hypotension. You can see here that patients with orthostatic hypotension are in the advanced stages of Parkinson's disease, but they're also under a higher medication dosage. Again, this is the signals we used in this study. We used ECG or heart activity, blood pressure, muscle activity, posterior sway, and respiration. And since we were interested in studying the causal analysis in the frequency domain, we first decomposed all the signals into their frequency content using empirical mode decomposition. Those frequency contents are noted intrinsic mode functions. And then we extracted the dominant mode in each frequency, the high frequency and low frequency band. And we used convergent cross mapping to study the causal relationship between these oscillations. So this is just a signal in figure A. The signals were recorded. And in figure B, you can see all the oscillation of these signals. And as we move from IMF1 to IMF5, the frequency drops. So higher frequencies are in IMF1. And as we move away, we get the lower frequencies. And this is a picture that shows the dominant mode in the high frequency and the dominant mode in the low frequency. You can also tell that there is some oscillation that are synchronous with a certain phase. You can see here in figure B that respiration has the highest power in the high frequency band, which is within the range 0.2 to 0.3 hertz, which corresponds to 12 to 18 breaths per minute. And you can see here in the low frequency that respiration is pretty synchronous with posterior sway and also muscle activation and blood pressure. This just shows the change of blood pressure from supine to tilt. And you can see here in Parkinson's with orthostatic hypotension, they had the higher drop of blood pressure. It's more than 26 millimeter of mercury. And that's why these patients were considered patients with orthostatic hypotension. In this figure, you can just see that the effect of medial lateral sway on respiration is lower in Parkinson's patients without orthostatic hypotension compared to healthy controls, and similarly for effect of anterior posterior on respiration. In this figure, you can see that people with orthostatic hypotension, they have a really lower effect of their muscles to maintain posterior sway in the medial lateral direction, and similarly for anterior posterior direction, has a higher effect of muscle activation in these patients. What I want to show in this figure here, we wanted to know which one is the dominant driver. Is respiration driving posterior sway more dominant, or posterior sway driving respiration to be more dominant? And it was found that respiration to drive posterior sway here in Parkinson's is more dominant than the opposite case. And this is for anterior posterior, medial lateral and anterior posterior sway in figure B. Moreover, respiration driving muscle activation was more dominant than muscle activation driving respiration. This just shows that respiration has a higher effect on posterior sway and not in the opposite direction. We were also interested to figure out if respiration has higher effect on the medial lateral sway or anterior posterior sway. And we found that respiration has higher effect on the medial lateral sway than interior posterior sway in healthy controls, but also in patients without orthostatic hypotension. So as a summary, we found that Parkinson's without orthostatic hypotension have a higher effect of respiration on the medial lateral sway compared to healthy controls. We also found that in Parkinson's patient, respiration-induced posterior perturbation mainly in the medial lateral direction. And also patients with orthostatic hypotension, they have a really lower effect of muscle activation to maintain posterior balance in the medial lateral direction compared to patients with orthostatic hypotension. And finally, I would say understanding the causality in the frequency domain between all the frequency counts of these signals could help developing appropriate measures to prevent posterior instability in patients, in Parkinson's patients. So in this last contribution, we were interested in studying the potential of using cardiorespiratory interaction and also the interaction between blood heart rate to first track the progression of hemorrhage, but also identify patients with low tolerance to hypovolemia. The current challenges for tracking the progression of it usually happens in the battlefield. For example, soldiers shot, they mostly die before they reach the nearest treatment facility. Another challenging factor is the current physiological markers do not really track accurately the progression of hemorrhage, and they change until the late stages of bleeding. Another challenging factor is there are certain patients that are naturally not tolerant to hypovolemia. So they have a low tolerance, and they will reach a cardiovascular collapse before the patients who have a highest tolerance to blood loss. So the purpose was, as I mentioned, first designing a system that can track the progression of hemorrhage, but also identify these patients that will reach cardiovascular collapse in shorter time, and these patients would necessitate sooner intervention than the patient who are high tolerant or they can tolerate higher blood loss. And because of ethical issues, we cannot just simulate hemorrhage by drawing, blood from patients. We use a non-invasive way called lower body negative pressure. Basically, what it does, it exposes the patient to negative pressures and translocate blood from the upper extremity to the lower extremity, simulating something that would happen in hemorrhage. And this is just the applied pressure and their corresponding hemorrhage staging or blood loss in terms of the volume that is lost. So as you can see here in this figure, figure A, you can see that blood pressure did not really track the progression of hemorrhage, neither in high tolerant or low tolerant. And similarly for pulse pressure here and the other pressure kind of values. On the other hand, stroke volume and systemic vascular resistance were really good indicators of blood loss. You can see here they could differentiate baseline from negative 20 millimeter mercury, which is mild hemorrhage, in both groups. However, again, they did not provide information about if those patients are tolerant or not. You can see here that inhale over exhale ratio, it really provided good information about distinguishing patients that are high tolerant from low tolerant here as early as negative 30. But again, this one did not provide information about the progression of hemorrhage. So it did not change across this LBNP stages. So in this work, we used interaction between blood pressure and heart rate. You can see here that we were able to differentiate rest from negative 30 in both groups, while this interaction between blood pressure and heart rate in the low frequency was pretty able to distinguish between high tolerant and low tolerant as early as negative 20, but also during the resting stage. Similarly, this figure provides the same information. Pulse pressure and RR intervals in the high frequency could track the progression of hemorrhage, while pulse pressure and RR intervals in the low frequency provide information about tolerance to hypovolemia. We also conducted a sensitivity analysis where we looked first at the overlap between the responses and also the sensitivity of these metrics. So you can see here that the overlap of responses here at 0% between rest and -40. And we achieved a sensitivity of 84% to differentiate rest from severe hemorrhage. And similarly for differentiating, sorry, go back. Similarly for differentiating here, rest from -50, the overlap of responses between the groups is 0, and we have a sensitivity of 95%. On the other hand, if you look here, our markers, they have overlap response of 15 and 2%, while heart rate has a higher response overlap, it's 80%. And we achieved a sensitivity of 75. We also compared our results to the existing literature, and our results are really comparable in terms of first tracking the progression of hemorrhage, but also identifying patients that are low tolerant to blood loss. So in summary, I would say that using the interaction, the physiological interaction between heart rate and also cardiorespiratory interaction could give a potential for this methodology to track the progression of hemorrhage, but also, as I mentioned, identify those patients who are low tolerant and would need sooner intervention. So I'm just going to list here the main contribution of this work. So again, we studied the cardiac and muscle pump function in Parkinson's. We studied the cardio-posterior coupling and the effect of respiration on posterior sway in Parkinson's disease. And we also proposed a system that can track the progression of hemorrhage and identify those patients who are low tolerant to blood loss. I just want to talk here about some limitation and future work. So in this study, our sample size was limited. So large cohort analysis would be useful to validate all the systems that we studied in this work. Also, our Parkinson's patients were in the early stages of Parkinson's disease. So it would be useful to see the effect of advanced stages on Parkinson's disease on the cardio-posterior interaction, respiratory and postural interaction, but also cardiorespiratory interaction. It would be also useful to include data from other muscles that affect posterior balance and respiration, such as hip and thigh muscles, which we did not investigate in this work. And finally, we did not have an indicator of how much blood was put to the legs when someone standing or during the TEL test. So measurement of blood pooling would be really helpful to give a kind of a relationship between the amount of blood pooled and the responses that we showed. And the main goal of this work is basically to be able to design a bathroom-like scale device that could predict posterior instability and prevent falls in people with Parkinson's disease. So this is basically a prototype of the CardioPost model that is being developed in our lab, and it's ongoing. It's an ongoing work and trying to kind of include all the information we learned in this work in the device, and hopefully can give us an indication on a risk to falls and be able to prevent it. These are some articles that we got from this dissertation. So there are currently 3 manuscripts published. 2 of them are submitted and under revision, and 3 of them are under preparation. I was also fortunate to participate in national and international conferences, and this is some publication that we got out of that. So before I move to your question, I would love to thank everyone who contributed to this dissertation directly and or indirectly. And first, I would start with Dr. Kuyar. I'm very grateful for all the support that you provide and the guidance throughout my PhD. Thank you for letting me do work in the Biomedical Engineering Research Complex lab. And I'm also very grateful for all the trips that you had to take during the winter, for data collection to Sanford Clinic in Fargo. Thank you very much. I'm also very thankful to Professor Joe Shin-Lu for allowing me to do research in the Parkinson's Research Lab at Sanford Clinic and for recruiting Parkinson's patients. Many thanks also go to Professor Andrew Blaber for all his guidance and technical support during my PhD, but also for allowing me to collaborate with the aerospace physiology lab at Simon Fraser University. I would also like to thank my committee members, Professor Rashid Ahmed and Dr. Boliang and Dr. Dan Ewart for all the feedback. Thank you very much. Many thanks, of course, to the School of Graduate Studies for providing me with the summer fellowship dissertation. to be able to focus on my work. And also, I would like to thank the School of Engineering and Mines for funding all my research during my PhD. Many thanks to the Fulbright program for allowing me to spend 1 year in the US and do research at the university. I'm also very thankful to Deerfield Catalyst for giving me the opportunity to spend the whole semester in their company and get exposed to the medical device industry. And of course, I would love to thank all the volunteers that dedicated this time to this research. I'm also very grateful to my collaborators who contributed significantly to this dissertation. I'm very thankful also to all the members of our Biomedical Engineering Research Lab and my friends. Many thanks to my family, of course, for supporting me, and also my wife for her guidance and all the sacrifices that she has made. And I'm sorry if I forgot someone, but thank you very much for all your help. Appreciate it. And I would be happy to answer any questions that you may have. Thank you.
So, we are open for questions. We'll start with the committee. Dr. Liu.
Should I save the question?
Cannot hear you. Or maybe
Should I? Can you hear me?
speaker is off, I think.
Huh? I think I'm mute.
I can hear you, yes.
Yeah.
They just can't
Someone
hear you
else
in the conference room.
The audience, Dan, can you talk?
Yeah, I'm talking, and we
Yeah.
can hear the questions
Yeah.
on Zoom.
We cannot hear anybody.
You cannot hear me?
Okay.
Maybe you have to mute your laptop.
Okay. No, this is the only way we can hear them.
Oh,
How about now?
okay. So
Can you hear
I
us?
mute
Kuya,
myself.
can you hear me
Yeah.
now?
Yeah.
Yeah, Kuya. So my question is, should I say my question to for the committee session and let the public ask question now at this time?
Oh, I think he's back to not being able to hear us.
Dr. Liu, go ahead. It is the committee's time, and please go ahead with the question.
Oh, it's committee time now? Okay.
Yes.
Okay, so my question focus on the muscles of lower extremity. So we don't record from the four muscles anterior tibialis, which is in the anterior of lower back, lower leg, and then gastrosoleus, lateral medial, and soleus all on the back side, which is ankle extensor, and then the anterior tibialis and ankle dorsiflexion. My question is that have we looked at the correlation of the muscle activity of those three muscles, lateral gastro, medial gastrosoleus? Do we need to record so many muscles, or just one muscle will tell us the effect of the muscle group on what the data we see?
Yeah, thank you. Thank you so much, Dr. Liu, for your question. It's a very interesting one. From what we found in this work, and as I can go back and show you. Just give me a, just.
Can you hear us? You guys there?
Yeah, I can hear you.
And somebody show me a thumbs up?
Yeah.
Okay, good.
So yeah, here. So as you can see here in this figure, yes, you can see that medial gastrocnemius and soleus are higher in both groups compared to the other ones. And these muscles are mostly used to maintain blood pressure during standing. However, it was shown that the tibialis inferior is mostly for a postural balance. So to respond to your question, yes, I don't think we would need to record from like all the calf muscles. In this case, it would be, I think, sufficient to record from medial gastrocnemius and soleus, these have a higher effect on blood pressure, but they contribute only to posterior balance in the interior posterior direction using the ankle strategy, as you mentioned.
Yeah. So you also mentioned that you
Yeah,
wish. So you also mentioned that you wish in the further direction now, you wish to measure the thigh muscles. So how do you think that those will contribute to the study we are doing? Is it will it be significant? Just you know, just you know, guess, you know. They are not as low as the legs in the muscle in the lower leg. Do you think the thigh muscle will be contributing to? Rabie, can you hear us?
Yeah. I was saying, Dr. Liu, that postural balance in the interior posterior sway is maintained via the ankle strategy that uses
Correct.
the ankle muscles, right?
Right.
However, the medial lateral sway, so if you move this way, it's mostly hip muscles. So, and that's one of the reasons here that you can see that posterior sway is higher in the medial lateral compared to interior posterior direction. It's because in the interior posterior, lower limb muscles contribute to maintain balance in that direction. However, in the medial lateral is more complex because you need hip muscles, and you also why it's more complex because oftentimes that you have to stand only on one leg, and that's give higher more complexity. So this balance in the medial lateral is kind of harder to maintain, and that's why it was associated more with falls in elderly people.
So that's a very good point. Then my last question is, so we look at our body. So we have, you know, thoracic area, we have leg area. Then one area we haven't touched upon is middle abdominal area. Splenic circulation, you know, is about 25% of total circulation.
Right.
And I haven't thought about it. And at one time I was trying to find some literature and not too much study on it. I would guess the circulation, the pooling of the blood in the splenic circulation is also very important.
Yes.
Is there any good way we can study it?
Yeah, that's a very, very good question. Yeah, I mean, most of the blood pooling occurs, as you mentioned, in the splenic circulation. I am not sure if there are ways to measure like how much blood is pooled, but I'm pretty sure we could look at certain biomarkers that give us information about blood pooling in that area. So,
Yeah,
but it would be very interesting to look at this because yes, most of the blood is pooled in the splenic circulation.
Do we know that anyone in the biomechanical area or the one from Dr. Breber's or anyone's institution, anyone study that? That would be very interesting.
I would be very curious if, yeah, go ahead, Andrew.
We published a paper on that, I don't know, 10 years ago or something, in LBMP showing splenic volume redistribution during hypotension. So I think it's in the European Journal of Physiology. It'll be in it'll be in my CV somewhere. And I think we use segmental impedance to get that information from the splenic region, but it also fits with my PhD student Hachia, who looked at volumes during standing and compensation. So people who didn't faint had better splenic redistribution during standing. So it's a good question, but typically when you stand, the pressure drops and you have an elastic recoil that redistributes splenic volume back to the central volume to compensate for volume in the legs. And we can talk about that later, but
Yeah.
anyway.
Thank you. Yeah. Okay. So I did as a committee member ask questions.
Thank you, Dr. Liu. Let's move to Dr. Blaber. Andrew.
So thank you, Rabie, for great years in your thesis and a presentation. I know they had a lot of work to cover here in a short period of time. So some of those who have not been coming to our biweekly meetings may have got a bit lost in the presentation, but it was I like the way you tied everything together. So I wanted to continue with a few questions here I have jotted down in relation to what you've been working on. First of all, we've already discussed many times the work for the first publication. So, and the second one I'll come back to a little bit later. But so if we look at, you looked at breathing, and from what I gathered, you talked about the relationship with breathing, and then most of the impact was on medial lateral sway. So could you explain anatomically why respiration would affect medial lateral as opposed to anterior posterior? Just what is the mechanics that would cause you to sway left to right versus forward to back when you take a breath in? Because I think intuitively someone might think that it might not be the opposite. It might be the opposite to that. So can you tell me why that might happen?
One way that I would think about it is when you're like breathing, it's basically, you know, those abdominal and thoracic muscles, right? And those muscles are mostly used in maintenance of medial lateral sway because they are kind of directly related, you know, as like when you move your hips, that's how you maintain the medial lateral sway. However, anterior posterior, it's mostly if you stand up and you move forward or backward, you're mostly using your leg muscles and thigh muscles. That's one way I would think to. That's why respiration affects mainly medial lateral sway, but also the posterior sway in the anterior posterior direction has many options. You have leg muscles and thigh muscles. However, the one in medial lateral is very complex to maintain, as I mentioned before. So does this answer your question, Dr.
Well, I was mainly interested in perturbations. So when you breathe, what happens to your center of mass? That's what I'm wondering, which one would be compensated more. How would you explain it from a mechanistic standpoint based on the mechanics of you know, the shape of the body as it changed while you breathe? Or is it just purely the muscle activation which drives this way? Or is there a change in the center of mass that would drive that compensation? So I'm trying to get a better understanding of what which mechanisms might dominate, and have you thought about that?
Yeah, from what I have read, it was mostly because of those breathing muscles that affect mainly the medial lateral direction, you know, using kind of the hip strategy. But I'm pretty sure there's also like a part of the autonomic nervous system that might branch with parts that maintain the medial lateral sway. And as I mentioned in the manuscript, that there's also areas in the brain that control respiration, but also there are branches that goes to lower limb muscle activation. So that's how I would think about it. But this is very good point.
Do you have that graph that shows this way? Because right now we're showing, I think it's a different graph.
There we go. You're talking about this graph?
Yeah, so that's one of them. So this is just showing the velocity in the different directions. So medial lateral velocities and displacements. Do you have the displacement as well?
No, I have only the velocity here, but the displacement showed similar behavior.
Okay.
Yeah.
And it was higher but even in the Parkinson's, I was looking at this, I can't see the significance here. Wait a minute, let me just move the picture of everyone. So the anterior posture was not significant from the controls, but the mediolateral was. That's the case, right?
I think they're both significant. And since here, you see the bar is like the median, but on average, if you look, there are some, the upper like 75% is higher than.
Right, it doesn't say here. Oh, I guess.
Yeah, it just
right
doesn't
in the
say.
text it does.
Yeah.
Yes. Okay. So they're both increased in this case. So do you have the muscle interaction now? Can I see that figure again?
Muscle bit with interaction with what?
With the sway.
Yeah. Yeah.
Right. Okay. So just moving back to Dr. Liu's question. In terms of mediolateral versus anterior posture, your conclusion was that blood pressure was more regulated in mediolateral compared to anterior posture. Is that correct?
Andrew, wait for a
Sorry, Dr. Baber, I didn't get your question. Could you please repeat it?
Okay, yeah, sorry about that. Some technical issues, but so your conclusion was that blood pressure was more regulated through the muscles in mediolateral versus anterior posture. Is that postural? Is that correct?
Yeah, I found that muscle activation had, first we found that medial lateral sway is higher than interior posterior sway, and muscle activation was more for blood pressure than posterior sway. Well, muscle activation contribute to maintenance of posterior sway in the interior posterior direction, but with limited effect on medial lateral. It's because it's used in the ankle strategy, while medial lateral is maintained via hip muscle activation and other respiratory muscles. So that's why leg muscles are more for interior posterior, and that's why they did not contribute fully to posterior sway in both direction, and they were more toward blood pressure control.
Okay, so the question I'm asking, and you demonstrated it briefly when you answered Dr. Liu's question. So mediolateral is, I think, in the postural, in the sway community, they call that catch and throw. Are you familiar with that term?
Not really.
Oh, okay.
Yeah.
So in terms of a model for control, it's basically you throw your body from let's say you're going left to right, you throw your body from the left leg to the right leg, and then you catch your body with the right leg.
Got you. Yeah. Makes
Okay.
sense. Yeah.
So basically you're not hopping because they don't leave the floor, but it's an activation of muscles in opposite time, in alternating times. So you don't have the left muscle activating simultaneous with the right. So you're not using the full muscle capacity of both legs
Right.
at any given time. Whereas anterior posture, you would be using the same muscles on both legs at the same time.
Right.
So that might answer the question as to why anterior posture would be more dominant for blood pressure than medial lateral, because you're in the medial lateral, you're only using half of the muscle capacity at any given time. Does that make sense?
Yeah, perfectly. Yeah. Thank you.
So I had one more question I want to ask, and I'll save the rest for later. Can you put up your the diagrams with the Venn diagram?
Sure.
I'm trying to figure out, get rid of everybody's picture on here so I can see the actual, there we go. Okay, so in the diagram, the red is the cardiac baroreflex. And we can see the effects that you talked about, it being reduced. Everything was reduced in, well, not everything, but that component, particularly in Parkinson's. And then can you go through me your description as to why the overlap is, what the relationship is between the overlap in the with the cardiac baroreflex with the other two components?
Yeah.
You see it's reduced in Parkinson's, correct?
Right. Yeah.
So can you give me some explanation as to why that might be the case?
Sure. So there's this like the red part here, which is the cardiac baroreflex. The green one is the muscle pump function, but it has two components. The component that is overlapping with the cardiac baroreflex is muscle activation, which is baroreflex mediated. However, the other component, which is like the passive contraction of muscles, and they affect blood pressure. So that contraction could result from like a posterior sway. However, the more important part, or the baroreflex mediated part, is the overlap with the cardiac baroreflex. And the overlap also is reduced in Parkinson's because we mentioned that they have a muscle pump baroreflex impairment, and that muscle pump baroreflex impairment could be attributed to the neural pathways of that muscle pump baroreflex that we have showed in one of the manuscripts. Basically, there are areas areas that control posterior are overlapping with areas that control blood pressure, and there is a branches branches from the nucleus tractus solitarius, the main controller of blood pressure and respiration, has also heavy branches to other nuclei that control posterior sway. So if there, we know that people with Parkinson already have issues with maintaining blood pressure. So if there's like impairment in one system, it leads to the impairment kind of the interaction between the two systems. So that's why muscle pump baroreflex is impaired in Parkinson's, and we can see it here in the overlap kind of portion between the red and the green circle. Does this answer your question?
Yep. No, that's good. Okay, I'll pass on to the next person.
Thank you.
Thank you, Dr. Glaber. We are moving to Dr. Eward. Dan?
Yep, I'm there. I'll just ask one question. I'll save other questions for the committee session later. So all of this depends upon your data that you've collected. And so one of the things that you said early on, Rabie, is that you used a 5 Hertz filter. Can you tell me more why you chose a 5 Hertz filter?
Yeah, definitely.
Can you tell me a little bit about what your sampling rates were?
Sure.
Also, I'm interested in any kind of, if you can recall, any kind of phase distortion, or what kind, depending on what kind of filter you use.
Right, right. Yeah, that's a very good question. Let me just go back to slides where I talk about that.
Sorry, I should have written down the slide number, but
yeah, thank you so much. So to answer your first question, the 5 Hertz, why? So there is this like Cenium community that kind of gives some guidelines for the sensors, also the perfect filters, and they recommend the filter of 5 to 20, right? But since we're interested in cardio-posterior interaction, which happens below 0.5, so that's why we chose a filter of 5, and we're including 0.5 in that. And in terms of the filter that we used, it's an infinite impulse filter, which is the Butterworth filter. It's a low-pass filter with a cutoff frequency of 5 Hertz.
okay. Do you know anything about phase distortion with that?
I think I looked at the frequency response, and it really matches what I wanted to do, but I'm not sure if I looked at the phase distortion, but the frequency response was very good and it was decaying, and at 5 hertz, there's that decay, and then I was like, okay, so that's a pretty good filter.
And then one final question just on this. You're
Yeah.
really interested in 0.5 hertz and below, right?
Yes.
So why did you choose 5?
Because that's just like, as I mentioned before, the like guidelines 5 to 20. So we just like chose 5, but that also include anything below 0.5.
Okay. All right, I'll save the rest of my questions till later.
Thank you so much, Dan.
Mhm.
Okay, so we move to Dr. Ahmed.
Hi, Fadil. Thank you very much. It was a great presentation. I really enjoyed all the time and I hear from you. Thanks for doing this.
Thank you.
I have one statistical question just to understand the process. So you mentioned that your series is some of the data are non-stationary. What kind of the transformation you used and to make it stationary, and does it have any impact on the transformation in your data?
Sure. Thank you so much for the question. Yeah, so the natural kind of think of physiological signals are non-stationary. So if you look at your heartbeats, every beat is different period. So it's by natural is non-stationary. And that's why actually we did not use stationary techniques that require that assumption, such as Fourier transform when we looked, for example, at the frequency contents of the signals, or causality, for example, Granger causality, which uses which assumes that the data is stationary. So to avoid this problem, we use techniques that can deal with non-stationarity data. So we use the conversion cross mapping that doesn't have any assumption on the stationarity of the data. It's based on space reconstruction, as I mentioned before. That's to study the causal relationship between time series. And similarly for wavelet coherence transform, it's actually doesn't use those sines and cosines as in Fourier transform. Those sines and cosines are stationary by definition. And so we use the wavelet coherence transform that doesn't assume anything about stationarity, and the wavelength itself is, can deal with the non-stationarity of the signal. So that's how we didn't do any transformation to the data to make it stationary, but we used techniques that could deal with that. Does this answer?
Is that technique depends on the sample size, and how the sample size variation is having an impact on that?
Yes, that's a very, very good question. Actually, conversion cross mapping, if I go back, it doesn't depend on the sample size, but it doesn't depend on the frequency, but it depends on the sample size. To give this figure, for example. So if you imagine you have like a larger number of points, this reconstructed manifold will be denser, and therefore the prediction would be better. So you have like a denser kind of manifold, and then you would reach that what we call a convergent cross mapping. So you basically converge cross map the two manifolds, and you can have a pretty good prediction here if your manifold is very denser, which means if you have a higher number of data points.
I'm good.
Thank you.
Thank you, Dr. Rashid.
So we are moving to Dr. Leon here.
Yeah, I have a few questions.
Yeah.
Can you go to the, just start with here.
Yeah. Right.
Basically, because I'm not very familiar with the new method we're using.
Sure.
You assume that you eventually have a number that if that number is higher than like the causal relationship will be more significant.
Right.
How do you do your validation? How do you know it's working?
How is it like significant?
Yeah, because for any data, you can get, for example, any signal, you can get a number. How do you know this is working and you have this causal relationship? You have some examples?
Right, right. This is a very, very good question. So if I just, let me just maybe go to one of the results and like, for example, this in figure B, just an example, muscle activation driving blood pressure, right? We know that people with Parkinson's, they already have issues with their muscles, right? They have like muscle rigidity, sometimes cramps or spasm and all of that. All of this, like theoretically, would affect the function of these muscles to pump blood back to the venous circulation and maintain blood pressure. And we can show this here with this causality metric. We can see that muscle activation driving blood pressure is lower in Parkinson's compared to healthy control. But there are other certain mechanisms that are known in kind of naturally known. For example, we know that respiration affects heart rate, but the opposite direction is less dominant. So when we use the technique and it gives us something that matches what is physiologically valid, then that gives us like a sense of kind of this technique is working. It's not giving us something that is, you know, out of context or it doesn't make any sense physiologically.
Starting this slide, and you're
Yeah.
saying that for the Parkinson patients, which is on the right, the red color, is lower than
Yeah.
the left. I noticed that you don't have statistic data, so it's not significant, or
I put this like cross marks here to show that it's statistically significant. Yes, yes, yeah. So the cross like Lorraine mark, significant difference between the Parkinson's patients and healthy controls.
also, yeah, I know that there's I read your draft. And,
Yes.
and please add the statistic, like what kind of statistic you have the figure item.
Definitely, yes, yes.
And now the second question would be, can you go to the one diagram? Like
Venn diagram? Yeah, yeah. Here we go.
I think this is a very good reason presentation of the data. And,
Thank you.
I was wondering, have you considered to use some more quantitative way to evaluate the difference in the healthy control of the Parkinson's patient? Because of course, we know the number.
Yeah.
There's purple,
Yeah.
the overlap of purple that they are
Yeah.
lower, probably healthy than the Parkinson patient, but overall, maybe you can use some method, these were are these two,
Right.
which two are more.
Yeah, yeah. That's a great point actually. And so if you look here, like the bolded text, so this one, for example, and this one are statistically significant. So the bolded text is the region that are statistically significant, and the one that is not bolded is not significant. So, but this is a very good point. Yeah.
One last question.
Yeah.
With this research topic and more like
Yeah.
methodology. So can you go to your last contribution? There's the last couple of figures.
These ones?
So yeah, I just, this is also a comment to this. Would that be easier? You just use correlation between like the X and Y, and instead of doing this
Right.
number, and this you have a significant correlation with that. You got kind of, you can simplify the overall data because you need to show curve. All you need to show is
Yeah, that would be interesting. Yeah, definitely. Yeah, it's a pretty good idea, maybe from the visualization.
got a lot of data.
Yeah.
And I'm overwhelmed. I know that.
Sorry for
Yeah,
that.
that's a lot of work. Obviously, I haven't attended your bi-weekly meeting for a while. I think you can simplify this data and the rest of the figures.
Right. Yeah, I agree. Yeah. Thank you so much. Yeah. Thank you so much. That was very helpful.
Very much for all the questions. I will ask my one question and related to what Dr. Leong was just talking about. So we had a trial presentation yesterday, rehearsal presentation yesterday, and I asked Rabie to reduce significantly the last contribution part because for the same reason that you just raised, there was so much results. There was so much a lot of work done and a lot of publications, and I thought also this is going to be overwhelming. So I asked him to reduce it significantly on the last contribution. But maybe, and now I just saw what he did in terms of reducing that part. But maybe to make some connection between your last contribution to the first three, because the title of the thesis is Parkinson's, and you have all of a sudden something on hemorrhage. Why you thought this contribution is related to the other three? Maybe going over that to clarify.
Thank you so much, Dr. Koyar, for this. So as I mentioned before in one of my slides, that orthostatic hypotension, it's very known to happen in people with Parkinson's, right? But it also happens in elderly people, and it could happen during severe hemorrhage. So it's a severe drop of blood pressure. So all this information that we used here, all this methodology, could be also applicable to track the progression of hemorrhage. It would be very important, to save lives, either on the battlefield when a soldier gets shot, but also in postpartum hemorrhage. A lot of women, after giving birth to a child, they may bleed overnight, and having markers that can track that progression of bleeding overnight and save lives would be of high use. So even this was for Parkinson's and healthy control, but those interactions between the systems, they have meaningful physiological information. And without this interaction, it could lead to failure even of organs or chain of failures. So that's why, all this that we use here could also be applicable for tracking the progression, as I mentioned, of hemorrhage, but also identifying patients with low tolerance. So this is just a slide I was referring to, that orthostatic hypotension, it happens in Parkinson's, it happens in elderly people, it happens in astronauts. So it would be very important also to monitor the health of astronauts using all these physiological interactions that have that are meaningful, as I mentioned, but also, as I mentioned, during blood loss. So that's what I thought. But actually, we have also, as collaboration with aerospace physiology lab in same Fraser University, and the same methodology is kind of being used and developed to monitor the health of astronauts.
So make sure you are mute. We are done with the first round of questions from the committee. Now the floor is open for the audience for any questions they might have. Enrique, go ahead.
Rabie, thanks so much for your presentation. I just had a quick question. Please forgive my ignorance if I say something that is completely wrong, but have you heard or do you know of any devices similar to GPANs that will help on the pulling of blood pulling that could happen from a sit to stand situation of a Parkinson's patient?
Yes. Yeah. Thank you so much for your question. That's very interesting. Yeah, of course, there are certain devices that could help with kind of improving venous return. So basically, there are all those cuff compressors that you can wear, and they compress those muscles, and they help a little bit with pumping blood back to the venous circulation. I know actually one of my coworkers had one of them because she always experienced that orthostatic hypotension symptoms. So yeah, I think there are those compressors that can help with kind of the muscle pump function. Yeah.
And just a follow-up, so I did some perusing around, and yes, I've seen some studies on what I call passive, which is like these either leggings or socks I was just curious to know if there's any kind of active ones, meaning if you are coming from a sitting situation to raising up, maybe at the device detects that, and because of that, it actually compresses the legs. I just don't know.
Yeah, that would be really interesting. I don't know any of these devices, but I think it's doable. I mean, if there's a way of measuring blood pooling, maybe non-invasively or estimated, and then produce response or a compression appropriate to that blood pooling, that would be really very helpful.
Thanks for the answer.
Yeah, thank you.
And I have just a small question on slide 72.
72, okay.
Yeah.
This one?
I was just curious to see that systolic doesn't change much, but diastolic raises when you have like negative on your x-axis. I was wondering if you could explain those results.
Yeah, that's a very important point. I think systolic, because there are many physiological mechanisms that are on systolic blood pressure. So you have your heart rate, you have respiration, and I would think systolic blood pressure is mostly cardiac contractility and vasoconstriction. That's my thinking about why. Well, but even though the systolic blood pressure, it changed until -40. So that's where you start to lose a lot of blood, and you need your heart to work harder. So you create cardiac contractility to maintain blood pressure and deal with reduced cardiac output. But this is a very good point. Yeah, I think that's my thinking why it happens, but I'm pretty sure there are other mechanisms involved.
Thank you.
Yeah.
Well,
thank you.
Anyone else have a question in the audience? Okay. At this stage, I will need to ask the audience to leave and the online people to log off. I will stop recording so the committee can ask their questions, the second round of questions, and then we will ask Rabie to leave for the committee to make the decision. Thank you, guys.